Awesome. All right, where we left off last time was the very, very brief introduction to kinetics. And again, the way I look at this is there's pieces. Understanding how to read a graph or a reaction progress graph like this is critical because you're putting yourself into both this conversation we had about assumptions about what these measurements mean, but also what's happening. And we talked a little bit about this concept of mass balance. The sum of each one of these data points is a constant the entire way through, and that's an important feature for you for doing other grounding. Think of it as a way of sort of testing if things like your analytical assay, if you are actually tracking all components, then that is a qualification that should be met. We talked a little bit about the visuals. You can extract qualitative information very quickly based on the changes in shape and key features of it. The ones I want to highlight most particularly is you're always watching for things like what's your initial concentration, your final concentrations, these are your yield. Conversion or percent conversion is your ratios between the components. Crossing points are usually important because those tell you things like at what point have we changed from 50% conversion, and things like changes in shape. The rate of the reaction are these individual little tangents along whatever the overall reaction function actually is. So when we say rate, and this is one of the things that first comes up when you start talking about kinetics, kinetics is all about rate, which is a change in time, so delta concentration over delta time. And usually the convention is that delta time is some small amount of time. So we're talking about integral calculus, basically, right? It's a Riemann sum kind of a question where we're saying, what is the change in slope of a line over some very small delta time on the reaction? And rate can change depending on where you are in the reaction. So the slope at these 2 points is very different just because the reactions are behaving differently here. Now, again, not a trick question, but give me a list. What is different about the reaction here versus here? So at position 1 versus position 2, let's list out everything that we know is different. Again, it can be obvious, but what do you got?
Higher concentration of A on lower concentration of B.
Right. So that explains rate being higher because it's got more fuel, right? You got more gas, it's running faster. What else you got? So again, let's focus it in terms of why might the rate here be slower? So first one we said is fuel, less starting material. What else? Why might rate at the second point be slower than the first? Right, if this was reversible, right, if this was not a unidirectional reaction, what we're saying is the increased concentration in B is pushing back. That's another way of stating product inhibition, right? That something is hurting the reaction because the product is pushing back. Now, we can get into validating which of these hypotheses are correct based on things like the shape of the reaction or multiple trials to say why, like maybe the language we're using now is maybe the reaction at the 40-minute time point is slower because of product inhibition. Well, if that is true, there are other things that should also match, such as adding B at the start of the reaction should similarly give you another slower reaction. We can come up with an experiment which tests that hypothesis. So the other thing too is that if we've drawn it in this general sense here, this usual point here, we're implying that it is A goes to B, it is a stoichiometric reaction. If this was catalytic, catalyst deactivation may be happening, catalyst death or decomposition may be happening, oxygen got into the system, there's other components. So this is one of the biggest problems we have when we talk about reaction mechanism is we are constantly going back and forth between vocabulary, which implies we know everything about the system and we're dealing with the simple, fundamental, elementary reactions, as well as we know nothing about the system. And what we're dealing with this is it's actually an observed reaction. There's a lot of unknown pieces under the hood that we're just implying they're there, we're not talking about yet. The reason I bring it up is because it's something that you're going to see over and again as we get into things like order. So mathematically, this makes sense. Most importantly, just like mass balance, what you have is an equivalence where the rate of one component as its negative must equal the positive of the other. What we're saying is there's a transformation of A goes to B, which means the loss of A must be equal to the loss of B. What is the condition that has to be met if this is true? This equality can only apply in one very, very specific, we have an assumption that's layered in on top of this.
The mass conservation?
Well, conservation of mass for sure.
That B is a product of A.
That yes, this becomes this, at least kinetically, there are no intermediates that are building up, right? That there's a single A turns into B and there's nothing else coming in. It's not just steady state. You're saying that, like, for example, you can have a steady state case where there's an intermediate B prime that might look like this over time, right? And in that case, yes, once you've hit steady state, the rate of product formation and the rate of starting material consumption will have a balance. But the mass balance won't make sense because you're missing a component of the reaction that the total sum of all species must include that point. So the graph here wouldn't give you that equality we said where the sum of B and A will equal the total mass balance. You'd actually have something, so for example, if you actually had an intermediate B star, we would expect that to come up, be flat over time and maybe drop off at the end, and that the total mass balance might start here, but in fact, if we were to sum every one of these points over and over and again, not including our intermediate, we'd expect it to drop off below and then rise back up again. So get like a bathtub shape of the total mass balance in the system. Again, we'll repeat this over and over again, but there's a really useful exercise to kind of go back mentally and saying what I am observing should look like the following. Here is the hypothetical graph I would expect given some outcome. That's the kind of language we're going to practice now. Copasi and these modeling softwares I mentioned are really useful at doing this. Now, again, just from vocabulary, we have some overall more complicated rate equation. What we have are the stoichiometric coefficients, which relate back to the mass balance. This is one reason why the individual rates may not be numerically equivalent because there may need more than one of some reactant or you're producing more than one product. So for example, if we had this general equation where 2 molecules of N2O5 are overall being converted to 4 NO2 and 2 oxygen and 1 oxygen, we have to tamp or otherwise balance the rates according to those stoichiometric coefficients. All we're saying is the rate of loss of N2O5 is going to be twice as fast as the formation of O2, and that's just molecular stoichiometry. This is the overall generality. This should be true. So when you actually were to graph this out, you would see that presented. The overall mass balance is still being conserved. What you're seeing though is this multiplicative thing where the rate of formation of our NO2 has a much steeper slope than the rate of formation of our O2. And that's just, again, back to our stoichiometric equivalence. So this is true, again, where in this case here, this balanced equation, has anybody ever studied this reaction before? It's a very classic one that they use for sort of gas phase kinetics and stuff. And it goes back to first year, where like N2O5 turns into NO2O2. If you had to think of the mechanism for that, like actually bond rearrangements, is this a single elementary step? What does your intuition say? How many molecules would have to get together in a single transition state to make that happen? That is insane, right? That's not likely. This is a multi-step cascade. It's actually a catalyzed reaction too. This is just one of those cases where the observed reaction you see down here is actually held because everything under the hood is so fast, or the concentration of these catalytic species is so low that the assumption of this is one elementary step and everything under there is sort of a K-obs does hold well enough for us to use it. And this is common why people are introduced to these more complex systems in gas phase kinetics with this idea that we can simplify it as one step. But this is what I mean about going back and forth. The overall balanced equation here has this mathematical relationship. We know implicitly that there's probably a bunch of transition states under that hood. We don't acknowledge it and we don't talk about it because under certain circumstances that simplification works. So the rate law that you get from the system looks like this. The rate law is actually just a constant times a concentration. Now, number one thing, everybody put up your right hand, left hand over your heart. No, right hand over heart, left hand up. I mean it. This is you're taking an oath. This is really, really important. From this point on, I will, thank you, everybody together, I will never use equivalence in a rate equation. In other words, if I have a reaction that's running with a palladium catalyst and I ask you, what is the concentration of the catalyst? You will never reply, oh, I did it with 1.2 mole equivalents, or I did it with 5 mole percent catalyst. A mole percent is a relative concentration based on something else. If I had a catalyst listed here, like, let's say 1% catalyst, that 1% catalyst is a common colloquial thing that all synthetic chemists talk about. It is not a concentration, and it implies that this concentration is relative to some other species. It is very, very, very dangerous because a lot of the times when people are first into kinetics and doing steps, I will run a reaction, I see you use 5 mole percent, I arbitrarily choose my initial concentration of this to be something, and it's different than how you ran your experiment. I do mine, you do yours, our data does not match, and we both point at each other saying, you're lying. And it's not that, it's just that you were not specific about this point. What I'm trying to emphasize, and this is one of the things that is really, really, really important. A rate law is a concentration times a constant. That's the entire language of any reaction. It's a constant which is related to the energetic barriers in the mechanism and a concentration of your starting material or whatever's burning in the reaction to make this reaction happen. And that's why, again, it fits where usually if we have some rate law, higher concentrations of one component and some rate constant will give you a faster rate. And this is also where gut feeling makes sense. Higher values of our rate constant, larger Ks, make faster rates. Those are faster reactions. So does everybody have a general sense of what you consider a fast rate? Like, what is a process you guys have all experienced that you'd put in the category of this is a really fast process? Give me an example.
Throwing sodium in water.
Okay, sodium with water, that's a good one. There's a lot of heat associated with that. I think that's probably right about the limit. What else? There's something that's everybody should definitely did it in first year, and you're probably not throwing sodium in water in the first year labs. If you did, you got a much cooler lab demo than I do. Acid base. Proton transfer is one of those things that protons reacting with a base is what we call diffusion limited, right? As soon as protons find hydroxides, bam, right? HCl and sodium hydroxide is kind of the limit of as fast as you can get. Do you know what the rate constant for that actually is? Like if you had to put a number on it, what is it? Guess. What's the magnitude? 1 times 10 to the bleh. What's that? 8? It's about 10, yeah. It's in that sort of range of like millions and billions, right? What about enzymatic processes? Like again, first year you guys have talked about this. A lot of enzyme biochemists, you guys for sure. Any other biochemists? Kind of. I was actually trained as a biochemist. The joke at the time was that biochemists used to brag about their enzymes based on their KMs and the rate constants. Like, oh yeah, I've got a KCAT of 1.6. What do you got? Well, mine's 2.5. Oh, you're beating me. No, this was, why it matters is it's an efficiency calculation. Again, I'm not going to cite it through, but something to kind of keep in your mind. Understand what numbers make sense, especially as you start to transition over to things like doing the modeling. When you do a kinetic model, any number fits because you're just fitting math. But if you did a model and your model said, oh, for your mechanism to be true, the rate constant which fits your data would mean that your K has to be 1 times 10 to the 500, you have done something wrong. There are some fundamental points, and you can kind of think of it where 1 times 10 to the 9 on the high side and 1 times 10 to the minus 9 on the low side, that is your operational window of normal reactions under normal atmospheric here on Earth type catalysis. Yes, out in the, either on the surface of the sun or in space, some of those numbers don't have to abide, but you can kind of think of that bracket of plus 10 to the 9, minus 10 to the 9, that's kind of your operational region. You'll see why that sort of comes up. It's a good number to grind. The same thing too is like, think of it, RT, right? Delta G equals minus RT ln KQ. RT is a fundamental constant of, God, what is R again? Ideal gas constant, thank you. And your temperature. Now obviously units matter for what those numbers are, but you can't beat simple thermodynamics, right? Now the most important thing about this rate law, other than this, that's our rate constant. What do we call this? That's order. No, it is. Like M and N are order. That and that are stoichiometry. A does not have to equal M, and B does not have to equal N. Does that jive with everybody? Does that surprise anybody? Why not? In your own words, why does stoichiometry not have to be order? Okay, there's no wrong answer. Give me an idea. What do you think?
Let's say it depends on the determining step and what reactions are involved in that order to be.
Yeah, it's mechanism, right? If this was a single step, one transition state, if these two or whatever species react in one transition state to make just these products, then absolutely there is equivalence between these two. Order and stoichiometry match as long as there's only one step. If it is multi-step, you can have zero order in one of these components, even if 5 of them have to be used in the reaction because the rate limiting step is somewhere under the hood. The reason why this comes up is for people that play in using kinetics to prove a mechanism, the number one thing people will go to when you're first using it is, I will determine the order in my catalyst. If my order in my catalyst is higher than 1, I have a bimolecular process. That may not be true. There's some very good fundamental examples where molecularity and order do relate, but it is not the rule. It is an exception, and we'll talk about that in more detail. So the first thing, and then this is why it gets weird. What I talked about at the beginning, we're using vocabulary, order of reaction, and we use that terminology, order, in a bunch of different ways depending on what we're talking about the mechanism. This is just a fundamental flaw of, honestly, the language of things like kinetics. If you're a synthetic chemist, you've been introduced to things in one way. If you're a physicist or a physical organic chemist, we use a lot of the same words, but the meanings are a little bit different. I'm just going to emphasize this in a bit more context. Fundamentally, definition. Order is simply, when we talk about order, we're talking about the rate equation, and we're saying that if I were to multiply or otherwise change the concentration of some species, what is the parity equivalence in change in rate due to that change? So if I double A and rate doubles, we have a 1-to-1 relationship between rate and the concentration of A, therefore it is first order. If I double A and rate 4 times, it is a squared relationship. I have a second order relationship in that point. But you do not have to be numerical. As we start to go through more complex systems, what you'll see is M and N do not need to be integers. What you'll see in this kind of version of the rate equation is what you may have something like A is 1.2 and B is -5. It can be any value because when you look at it this way, this reaction order definition, the rate equation as expressed here, we kind of call this the empirical or otherwise experimentally determined rate equation. We usually get this value expressed in this simple way of rate equals K times some concentrations raised to some power by doing multiple experiments such as initial rate measurements, and we're extracting that relationship. I will change A, I will measure rate, and then I see how does the variation in the concentration of one component affect the rate in terms of some multiplicative way. We're not really implying mechanism yet, and there's more than one mechanism that may fit what you observe here. So it has to be back and forth. So this is where we're looking at this overall change in time as we go through these different components. The integrated rate law, the other way from this. This is where we can go through and actually break this part down by saying, look, if I know that stoichiometry says there should be a 1-to-1 relationship between the two, as long as this is a elementary step, one transition state, then I can immediately derive from the reaction what rate law I should see with no other experiments. But if I have a rate equation like this, so very simple reaction where I know the rate equation is rate is equal to K times concentration, we can go back through and extract the order. So really all we're saying here by math, right, we're saying D concentration dt is seen here. That's equivalent to our rate constant K and A, which we'd extract from our experiment. And if we express the integrated form, we're just carrying out the rearrangement and algebra plus calculus to derive what the first order rate equation comes from this. This is not something that we're going to test in. This should be familiar. You've seen this part before, right? So back to first year and anything else, you're usually taught, I can identify that this is a first order rate equation because the exponent associated with A that I've measured experimentally is 1. That is true. It is first order in A. If I have a reaction where rate is equal to constant times A, it is first order overall. This is true, which means this is true. It's just forming it in the integrated form. Now, why do you think expressing, instead of rate equals K times A, what's useful about having it in this integrated form here? Yeah.
Linear plot.
Linear plot, right? This goes back to, again, another joke about physical organic chemists. People did everything to equations because graph paper was cheap and computers were expensive. So getting things into straight line relationships allow us to actually say, if I have something where I can plot y and x, and if I know two things and I know it's a linear relationship, it allows me very simply to extrapolate in both directions about what might happen with no other information. Linearizing things like this was useful just because it allowed us to both predict the future, but also look into the past as well. The main reason why these kinds of rate equations are very useful is because given any initial concentration, I can predict what the concentration should be at some time with a very simple reaction. No other math, no other graphing. It's just a linear relationship where if I know where I'm starting and I know my rate constant, I will know where I will be. And this is really important for things like, let's say you're sitting in a plant. If you are operating a reactor and you know it is safe to go home once the starting material reaches a certain concentration, you can go to this equation and say, I can go home at 3:30 in the morning. Right? That's one of the applications. The other way of this is, if I make two measurements, my initial and my concentration at time, I can extract my rate constant. So this is a 3 unknown system that allows you to either extract very simply my rate constant by measuring these two, or by knowing your rate constant and your initial, you can calculate where I will be at some fixed period of time. That's why these integrated rate equations are useful, but the assumption, this equation only applies if you're talking about a first order reaction. So these are the other ways that you've probably seen integrated first order reactions. This is the linearized form where we usually will plot this as y equals mx plus b. The slope is your minus k. Your y-axis is going to be your ln of your concentration of A. And then the other manipulations give you things like your half-life equations and things like that too. The important part of this is, okay, so this is what it looks like graphically. If you're sitting there and watching the reaction in real time, your concentration versus time profile will have this very characteristic exponential shape. It starts off faster, rate is falling off, and the literal shape that you have has this first order look. Now it's something as you start to work through this, again, after I was reflecting the other day, I've been doing this now for 20 years. Actually, as of December is when I defended my thesis. I've gotten to the point where I can look at a graph like that and it either feels right or wrong. Like the shape of this, you can see very quickly that this is not or it is first order just based on how it sort of appears in that point. But it's a lot easier if you can linearize it. You plot ln A and time, and do you get a straight line? That is an unambiguous way of saying I am dealing with a first order reaction. But really, that's it. If you've ever dealt with these plots of ln A against time and to get a straight line, you're doing what's called usually a first order reaction test. You have measured the concentration of A at a bunch of time points. You then plot the logarithm of those measured concentration A, your starting material, and then you're saying, does it fit to a straight line? So you're not only extracting the rate constant by finding the slope, but you'd also usually do an R-squared test to say, do my data points actually fall on a straight line, or are they curved, right? You can get cases where the data does not nicely plot across a linear series. And then from that, you can sort of say, I'm probably not dealing with only a first order reaction. It has a higher or lower order from there. So these are some of the more classical ways that you've dealt through. So just reiterating that, recognizing a process graphically, even if I have a species like this, 2 different starting materials plus a catalyst, what I can get there is something that looks like this. So, questions. If you assume that your initial concentration of your A and B is identical, what does that plot tell you? What's the order in A, given only this data? Okay, so we got 1. Everybody else? 1. Oh, come on, take the bait. Does everybody feel like, yeah, this is 1. It should be dead easy, right? Half? Again, I'll go back and forth. That's what I said was absolutely first order. That's this. So the shapes look the same, right? The answer, what's the order in A? I have no idea. Yeah? That's where let's start. Let's start here. I'm showing you, here is what A looks like over time, right? It's got this nice drop. Product over time, as I was blabbing about before, that has that first order shape, right? A plot of ln A versus time lays on a straight line. True. From this plot, I can reasonably say that, yeah, the slope is minus k, also true. What would the curve of B look like? What's your guess? If you said, for this reaction, if this is the overall reaction I'm going to follow, and I'm saying this condition, the concentration of A and concentration B initially is the same. If I had to graph that on here, it would probably look like this, right? It'll lay right on top of the A curve over time, right? Why do I know that? Like, why is that a safe assumption? If I start with the same concentration between both, stoichiometry, for every time I use up 1A, how many B do I use up according to this balanced equation? 1. So if I started with 1 and they have the exact same concentrations, as I chew up A, I must also chew up B. So I can reliably say that even though I haven't measured it, if this assumption is true, the curve for B against time probably looks like A against time. So if that's true, what would this look like if I did ln B against time, given that these curves are the same? What should this look like? Same. This says it's first order in A and in B. What would that have to be? If that was true, it is first order in A and first order in B. What is the overall order in this reaction? What is the order of the reaction? If this is straight, it's got to be a first order reaction. If it was second order, what happens, again, implicitly, what happens in a second order reaction? As I use up one component and another component, it gets slower a lot faster because you're kind of using up 2 things. The rate falls off much quicker. Just like if you add material, it gets a lot faster because it's A to the squared rather than A to the 1. You have no idea how many times when I'm reviewing journals, I get to basically copy this lecture and just hand it back to them because everybody gets this wrong. Because we start here, this feels good. Oh, it's first order. You can't tell from one experiment what the order in either of the 2 species is. These data only tell you that the reaction is a first order process. It is running according to a first order process. Something in here must be first order, but I cannot differentiate what that thing is. Something has to be first order. Something also has to be zero order in that case. And I don't know, based on the information provided, if it is first order in A and 0 in B, or first order in B and 0 in A, or heck, it could be first order in catalyst and 0 in both starting materials. But something is first order. One experiment cannot determine. It's a linear series of equations where I have 3 unknowns and I only have 1 variable, so all 3 are equally good. Yeah?
Steady state approximation here to figure out what the order is?
Not from this either. Like, you would have to derive the mechanism. Steady state approximation helps you to solve, but again, given a single piece of data, if this is all you know, all outcomes are probable. The only thing you can conclude from here, from a graph like this one, is I know it is a first order process, but I don't know what that thing, what's driving the bus. I have to go back and run 2 other experiments where I vary the initial concentration. Like if I go back and I vary the initial concentration of B and the thing does not blink, nothing changes, it is absolutely 0 order in B, because if I change B and the rate just says, cool, I'm not doing anything, B had no impact in the change in rate. Changing B does not change rate, it is 0 order in B. That's for sure. But this is not enough. And again, I bring it up because it is one of the most common errors when people are submitting kinetic data is they've done that point, single experiment, I'm making multiple conclusions from the same thing. It's not true. What is this? What's the only thing you can conclude if you're plotting ln A against time and you get a graph that looks like this? It's not a first order process. That is it. Stop. You might have a small region where it is obeying first order kinetics, maybe here, or possibly here, where it is kind of linear. But what you have is the reaction is changing. The order dependence in this initial, or this piece right here, these early time points, is not the same as over here. So both of those two things are true. The graphical thing, the sort of linear test that you guys may have been most familiar with, is not a black and white determination of order. They're more these kind of programmatic determinations, okay? Does that bother anybody? When I get your papers to review, we'll see. Okay. Yeah, so this is back to that same point. Again, given only this, order in A and order in B, we don't know from a single component. And I'll show you guys in Copasi how to sort of determine it discretely. Where this comes back is if we go to second order processes. Now we'll start with the simple system. We are saying it is second order and I have 2 species. It's bimolecular where the same thing is being used. It is also second order if it's A plus B, but the math gets easy to show it this way. This is probably what you guys have been taken through. So 2 molecules of the same thing are reacting. This is that rate equation, right? The change in concentration or loss in A is equal to A squared. Again, we can derive this if it's a single unimolecular reaction. We could go directly to these 2. From this equation, rearranging it, that's the integrated rate law we get. Once again, it's showing it as concentration and time. So they're in that sort of, just like in the first order one, we're using this linearized version to both predict what the concentration should be, but also extract the K. And what you'll start to see as soon as you get beyond the first order system, when we get to even something even mildly more complicated like this, these linear tests become really bad at extracting Ks because they don't work under all circumstances. One very important thing to measure, and you'll see this in different textbooks, 2 of A reacting with product graphically will look like this. Both of these 2 derivations are true, where 1 over A is equal to 2 KT and 1 over A is equal to KT. You've probably seen both of these ones on sort of like Wikipedia, whatever. And the number one thing I got teaching 123 first year was, well, wait a minute, no, my textbook says KT, you said 2 KT, which one is right? Why are they the same? It's a perspective problem, right? Basically, the mathematical derivation says, if I am looking at the stoichiometry with respect to the formation of product, this is what I will look like. So the formation of product versus the rate of disappearance of A, the K value you're talking about is not mathematically the K value, or the same K. 2K1 is equal to K2. And that's just saying I'm looking at the reaction this way versus I'm looking at the reaction this way. And that just goes back to what fails implicitly here. Mass balance says the rate of disappearance of A, here in blue, is going to be much steeper, twice the slope of the rate of formation of product. And the K, the slope of that value, is going to be more shallow. It's going to be half of the rate of disappearance of A. So this goes back to, again, where don't treat these as absolute in iron. Generally, these are the same kind of treatments. The linearized version, now you're plotting 1 over the concentration of your starting material against time to get a linear plot. That linear plot has a slope The K is your slope of this value, and again, it just comes where it's not the negative slope because of how the integration actually sits up. Now the bad side about this is these graphical plots only work if you're talking about A reacting with A, or identical concentrations of the same component. The second you get more complicated, where you have A plus B, or different concentrations of the two, these simple linear tests start to really fall apart. This is still a first order plot. The integrated rate law of just even something like this, where I have two different species, it is still second order, first order in each, but it's not going to show the same graphs as you have here, because first of all, I'm not reacting 2 molecules of A to make my product. I'm reacting 1 molecule of A with 1 molecule of B to make my product. So the math gets much more complicated. The reason why this is where things like the modeling software becomes much more useful, or what you guys have probably been introduced to is the idea of pseudo first order or pseudo zero order kinetics. So again, in your own words, what is that? What is a pseudo first order or pseudo zero order case? What are you doing or implying? Yeah.
Make the concentration of the one you're not analyzing high enough that you can say it's constant.
Exactly. If I can take this and make B versus A, my idea is that the change in the concentration of B over the time regime I'm looking at is approximately equal to 0, right? I'm saying that, oh wow, that is the worst color I could possibly put on there. I apologize, guys. I'm saying that if I make the initial concentration of one of the things so massive that because it is small in terms of its change, then it's basically constant, in which case K in that case is including. The K here would be what we call our K observed, which is equal to the real K of the reaction multiplied by the concentration of the thing we're holding huge. We're just putting together two constants in this sum, so the observed value we actually see is this multiplicative thing between the two. Or pseudo first order just means by making one super big and effectively zero order, the other one is our first order component. Why might that be a problem? And this really comes up in kinetics, in catalysis in particular. If you're trying to run a reaction and somebody told you, oh, this is easy, just make B very large. What is the quantitative value of very large? I mean it. This is actually where I started my postdoc, when it was like, oh yeah, just make B very large. What do you mean? So think about it from a tactical point of view. Make a decision first of all. What would you do? If you were presented with that challenge of, I need to run a reaction where I'm making B very large, where do you start? What do you want to do? That's probably the best tactical, right? We are doing this by saying, I will hold B large such that changing B does not have an impact in the rate of the reaction, right? So I will run the reaction at 1 molar in B, and then same concentration A. Then I'll do it at 1.5 molar in B, same concentration of A. If the rates between those two experiments do not change, B should probably be large enough that changing it does meet this condition where the change in B does not impact the rate. That's the analytical way of doing it. Have you guys ever heard of a rule of thumb that you should probably follow though? So that's one of the first assignments we're going to test out, is I want you guys to analytically come up with a suggestion. Usually it's 10x is what people say, but analytically, if you're actually trying to run this for some experiments, you will be running your reaction in B very quickly. Right? This is where you start hitting points where the concentrations you would have to hit, especially for other than enzymatic catalysis. You hit a point where it's like, I have to run this where I now have to start considering activity constants in my calculation for concentration. So we're way outside of what standard molar concentration even means. The viscosity starts to change. Dielectric constant starts to change. Pseudo zero order experiments absolutely suck for any type of synthetic organic chemistry, just because we have to operate in concentrations which are totally unrealistic. You will learn about your reaction, but you learn about your reaction in an environment which has nothing to do with how you would ever run that reaction. So it's not really relevant. Yeah?
What if B is expensive?
That's even worse. Then you're basically going to your boss and saying, yeah, I can run this experiment for you. It's going to cost you $40 million. It happens. No, we're doing this process right now where we have a visiting student coming in. They want to do a full kinetic analysis. Their catalyst they want to interrogate, they can make the Kingley sum of 20 milligrams. Over months of material, they can make 20 mgs. We go through the math and saying what weight, volume of catalyst we would actually need to complete this experiment, and it's about half a gram. So now you're staring down and saying, your boss wants a kinetic analysis. You are the student. You need to go make the equivalent of 100 times of what you've ever been able to do to potentially execute this. Is that worth your time and energy? And that's where all the other things we're doing in terms of analysis, other techniques, other points, have to get at this information because reality intersects with physics at some point. Okay, so we talked about that part. Last one to end off is zero order. Zero order just means there is no impact on either the individual concentrations. So no matter what the balanced chemical equation is, rate is just equal to a constant. Changing concentration does not impact the rate, in which case the integrated rate law is really simple. You're saying that you just have a straight line. This is simple, y equals mx plus b, where the only thing that changes about how fast this reaction goes is the rate constant of the reaction. So when you linearize it, it looks really simple. Concentration versus time is just goose egg straight line. Now, everybody should have in the back of your head, what is the classical example of a zero order process? Something that you probably have seen, again, so if you had to sort of match these, what's a simple first order process you probably have seen somewhere? It's probably the number one thing that you studied in first year kinetics. The classic first order process people run into, radioactive decay, right? Half-lives and stuff all derive from assuming that radioactive decay follows that process. Second order, we have a couple dimerizations and things like that. Zero order, something that just happens according to some constant, not concentrations. Photosynthesis. Turn light on, reaction happens, done. It is one of your basic sort of first zero order kind of processes. The other thing too that's weird about zero order is this does not match any normal organocatalytic reaction. You expect any reaction that has some sort of a mechanism looking like this is going to have some kind of a change in concentration due to the starting materials. There's not a lot of chemistries that based on very normal kind of like things like the Platinum catalyzed cycle, cross couplings or things like that, that fit a zero order model. It's possible, but it has to be something that it really doesn't matter how much starting material is changing. It has to be something where an intermediate usually is running this whole reaction. Everything piles up and waits for that particular point. So that's where we're going to end off today. We're going to talk through some of the basics of overall reaction processes. So we will review through this part here about just general energy surfaces, and then that's when we'll transition over into COPACI. So bring your stuff ready. We'll do a first introduction to what COPACI is on Friday, and I will see you guys then. Any other questions and stuff, please, happy to talk by email. See you guys.